Hi everyone, let's start. Thanks for coming. We're very pleased. This is like an experiment, so there are two guys giving this talk. I'll be the first one. Apologies, I won't be speaking at all about Spring, so I'll be talking about like a very broad introduction to deep learning, and then Dimas will be in charge of more detailed implementations of these things. And what we are trying to do here is like combining deep learning and a particular library in Java, DeepLearning4J. It's kind of, many of you may have used it already, but in case, I think it's like a very good library. I've been using other ones in Python and the like, and it's quite impressive. And let me tell you about a little bit my background. I'm a physicist. I've been working in numerical methods, and I'm currently working on the Supercomputing Center in Barcelona. It's kind of the national lab of supercomputing. So I'm not really in the implementation part, but most on the research and well, applying this to many different problems. So, okay, let's start. This is a little bit of the agenda of this talk. Will be, like I said, a very broad introduction to machine learning. It's not that, I mean, most of you already know a lot, but it's just like trying to link to the implementation we'll be showing afterwards. Then will be like an introduction of this particular library, DeepLearning4J. And then the implementation of an optimization of a neural network using the tools that Spring provides, in particular Spring Boot and the Spring Boot Actuator. We showed some lines for a... Same, yeah? Okay, good. And then a sample application and some conclusions. Okay, so this is like the machine learning part. Okay, so when you face some problem and you want to solve it with machine learning, let's say that you are driven by data and the kind of data you have. Okay, let's say that you have data which is labeled. Then, of course, you may be using supervised learning in order to train a model using these labeled data. But what if you don't have any labels or your data is just like raw data? You can still use a lot of machine learning tools and methods and do, for instance, like some kind of unsupervised learning, like classification. I mean, many times you classify things without being sure what these labels to classify things should be. And then there is another like leg on this chair, which is reinforcement learning, and this applies to situations where you have like an interaction between a system and an environment, and you will have like a sequence of decisions that will take you from one state to another one. We are going to talk about deep learning, and deep learning applies to many different techniques on these three legs of machine learning. In particular, I'll be focusing on supervised learning, but for no reason. It's just like it will allow us to introduce some details of the things. But these are very broad techniques. So let's focus on supervised learning. As I said, we require a labeled data set, and by label I mean we need some examples of a correct solution of the problem we are facing. The task we are trying to solve is to predict this label for unknown instances of the data set. And the key thing here is we try to generalize from our data set to like any instance we may face, which is unknown at the time of training. So we will be using a neural network. In this case, will be parameterized by a set of parameters. This can be a huge set of parameters, like millions or tens of millions, and then specifically only to describe the neural network. But then there will be other parameters that will describe the general architecture or many other things. And these will be related to the project we are showing here. And then we're trying to optimize these parameters in order to minimize the error between our predictions and the data set we have for the training. And then the overall picture of these methods is we try to find this optimal data, this optimal set of parameters. So I'm not going to be like really detailed on this, but basically the unit cell we are using here is a neuron, which is, let's say, very, very loosely inspired by biological structures. And basically we have a set of inputs and an output, and these are processed in a let's say two-step function, one which is linear and one which is not. And this, by combining these, as many inputs can be the input of different neurons, and the output of neurons can be the input of following ones, we can actually combine all these elements in a very general way. We normally do it by layers, and each layer is only connected to the following one. But there are already examples of like networks that may skip a layer and connect with the following ones, and also back connecting to previous layers. I'll talk about that. So let me focus on the applications of these methods. I mean, it's just like they are everywhere. You probably open the whatever blog and you will find a new application of this method. So I'm not going to be like very detailed on this. The interesting thing is you can classify I would say there is an important classification of the scenarios you may find with your data. One is one instance of your problem doesn't have to do with any other of the instances. It's just there is no dependence. And then there is situations where you will have dependence. Let's think of the example of classification of pictures. You may need to label a picture just to identify the item that's appearing on this picture, but you may also be trying to classify like pictures that form a movie, like frames of a movie, where each picture will have some relation to the following one. And then this will bring some dependence on the network that we may exploit, and this is really interesting. So one of the like more powerful properties of networks is how they can use the same information to to analyze pictures. And the basic example is the convolutional filter. The convolutional operation is basically like a small filter that will not depend on the size of the full picture that you are trying to analyze, that will be applied equally to all the points, more or less, of your picture. Basically, this is like a kind of convolutional filter that will apply in this situation. We have like three channels for our picture. Let's say that's a color picture, and we have 3 channels. And the same filter will be applied to each of these channels. And only we have to find the weights here that will optimize our labels. These filters here, these convolutional filters, can be found by hand, like you want to identify lines in your picture, for instance. But as the problem gets more complicated, we have to optimize the actual value of these filters in order to find the right labels. And of course, each layer of our network will have a different set of filters. But the good thing is that these filters are really small, and we only have to optimize these weights. So in this sense, if your problem is fit to this kind of solution, it's very effective. So this is the root. One of these filters will appear on each of these layers. And today we are facing like situations where we need hundreds of layers to solve problems, like classification. This actually is the winning instance of a problem where you have to label a picture according to what appears inside, with hundreds of possible labels. So, but what happens if you have any kind of dependence on your data set? And I was thinking about like, oh, we have these labeled pictures, so we have the picture and the label, but actually any time series is a labeled data set. So imagine you have like a text. The label of a subsequence of this text is the following word or the following character. So actually we have already a lot of labeled data sets for free. And actually the only thing we need is to have the only thing. It's just like a big only. Is we need some dependence between the information that we put inside the network at a given time and the following instances that will appear. So we can see this thing as a network where we don't have only connections to the following layers, but also to the same layer. And we can see that, for instance, if we assume that this is the input at different times, there will be some dependence between the information processed by each of these neurons and the information that the next step will face inside the process. And all of these things are the outputs. And you can assume that a correct model will predict this output to be the same as the next input we are inserting. Interestingly here, if we, for instance, are working with text for some instances, each of these elements can be a word or a character, and for many different scenarios, a very basic description in terms of characters would be able to raise the complexity of natural language, for instance, in terms of words and conjugation of verbs. So this is very interesting. So of course, this can be really complicated, and each of these neurons is not only like a linear and an activation function, but can be like a complex connection inside of each of these neurons. Fortunately, libraries today provide all these for free, so we only need to know that each of these correspond to like a processor of a recurrent neural network element. So that's all we need to know. So the overall problem is just we are trying actually to find this function, but this is like a very black box, and we only have access to a few of these x and y. A few may be like thousands or millions, but of course we don't have the full behavior of this. So we parameterize this function by some weights theta, and we can control this function f star, and we want to minimize the error between these two. Okay. So we compute this error with this loss function, and then once we know the error we are producing, we can update the weights by means of an updater function. So actually, there is like a lot of these functions, and actually, it's nice to have all these libraries that will provide you a way of changing this easily, because some of these are really problem dependent. I mean, some of these functions will work very well on some problems and will fail completely on others. So you can picture this you have to imagine that we are optimizing over a manifold that's defined by all these weights. Actually, it's a very highly dimensional manifold, and the updater actually is trying to find a global minimum on this manifold. This can behave completely different in a different way for different optimizers, depending on how do we define this manifold, and also how far we are from the global minimum. So some of these may work really fast at the beginning, but then fail completely when we are close to the solution. So it's always like a good practice to try a different of these, and that's the job of your library of choice. So what happens when we are training? We have a data set, and we have to split this data set in a training and a test data set. Of course, we don't want the training process to mix with the test data set, otherwise we'll be like providing information that we don't want to. We will be failing on our error computation. But actually, the typical situation may be that you visit. This is like along the training of your network. Epoch means to just like a single visit of all your data set. So actually, you repeat a lot this process. And you keep always, like, as this is like an optimizing process, you will keep improving actually over the training data set. When you evaluate your accuracy of the training, you will see that it's always improving. But actually, when you compare with the test that you are not using for the training, this may be, there may be a point where you are losing the generalization power of your network, and you are getting like this overfitting. So for really large data set, you may always be around here, but for a small data set, you may be perfectly here. What it means is just you are very good at predicting what you already know. Okay. So up to here, we are only optimizing the parameters that define the network, but there are actually many implicit parameters that we are taking by granted. For instance, the number of layers. Actually, the full architecture we are choosing. This can be like a convolutional, but could be like a fully connected network, could be like a recurrent. So actually, you have to choose all these things. The byte size for really large data sets, you cannot like analyze the full data set at once. You have to just like split it in batches. So this is like another choice, and this is like an important one. Then regularization, which is how do you correct your loss function in order to have like a controlled set of numbers that define your model. The learning rate is, besides choosing the method, is just how fast you allow this method to improve your weights. All these choices are outside, let's say, the inner loop of the optimization of the network. And then which are the initial values of your weights? All these things need to be optimized as well. It's just like an outer loop of your method. And actually, the project we propose here is just like how to do it with Spring. And just to finish, let me show you like some directions. I would say we are really reaching to a point where we can actually analyze things as complicated as raw audio, like with the raw signal of audio. It's just this is the ImageNet I was showing you before. Some solutions. It's just like this huge data set of pictures labeled with the contents of the picture. And then interestingly, there are like many new sources of data, like for instance, biometrics, where you have faces of people which are labeled, and then according to some like filters that you can apply to these pictures, you can extract some properties of the person that pictures in the picture. So I'm going to hand this thing to Dimas.
Okay, thank you, Artur. Now I want to introduce you Deep Learning for Java. Deep Learning for Java is a very nice library to work with neural networks. One of the problems that we Java programmers face when we want to work with machine learning, that's the most libraries, most tools, most frameworks are built on Python, on Lua, or in R. So Deep Learning for Java is here to cover our needs to work with machine learning when we are Java programmers. What do we have with Deep Learning for Java? Deep Learning for Java is, of course, open source and is one commercial grade and very established library which covers most of the most popular algorithms and topologies that we work on with machine learning. You have here the simple math machine, deep belief, deep autocoder, or other algorithms. It can work with Hadoop and Spark. This is a very interesting feature when you want to work with big data sets. One thing that Artur mentioned already, it's very common to work with pieces that you want to combine with working with big neural networks. And Deep Learning for Java supports also combining these spaces to make even more complicated neural networks using small pieces. I don't know if you know, but one of the problems that machine learning faces recently is that you need to make lots and lots of parallel processing. Current CPUs are not able to handle that amount of parallel processing. But fortunately, we have GPU. GPU are a kind of processors used for graphical processing that are composed in some cases with thousands of processors, very small with very big little capability, but you can have thousands of them. So you can parallelize a lot when trying to train a neural network, for instance. There's a very established library that is called CUDA that lets you to integrate with CPU processing, and fortunately, Deep Learning for Java is integrated also with CUDA. So you have parallel execution, you have parallel execution at GPU level and at cluster level. One of the features that most libraries that work with machine learning have is writing the most basic functionality in very powerful scientific libraries. Maybe you know about the CFI, that is a very powerful scientific library used for machine learning when you work with Python, that basically is able to make very powerful computations of manipulation with matrices. Matrices are one of the fundamental tools when you work with machine learning. So you have INDE for Java that we could call this the CPI version in Java, okay? One of the other problems that you need to solve when working with machine learning is how you code the information that you want to treat as a data set to be processed by your neural network. You have images, you have sounds, you have videos, you have whatever, and you know to code this information in a way that it's, if you remember, for instance, in convolutional network, you need to represent the information in some way where you can make reasonable sums in areas of this information. So this is called vectorizing the information, and you have a library called DataVec that lets you transform the information in a way that is nice for the neural network to be ingested, okay? You can transform CSV, images, sound, text, video, time series, and lots of other formats. One of the other nice features that Deep Learning for Java has is that you can not only train your neural network, not only experiment with your neural network, not only experiment with how to model it and work with it, but you can visualize graphically how your neural network is progressing, okay? I want to show you 2 slides. This is a kind of graphical visualization you can have when training your neural network. You can see how the the training is evolving, how accurate is your neural network, at which speed is learning. You can see the structure for the neural network, and you can experiment with your neural network, adding more or less layers, adding more or less neurons, and in a sense, working with the topology of your neural network. It's really a very, very nice tool to work with neural networks. Of course, other frameworks have these capabilities. Another thing that is very nice from DeepLearning4J is that it can support the models stored in other frameworks, like, for instance, Keras. Keras, I don't know if you don't know about Keras, but Keras began as a machine learning library, but nowadays is mostly considered as a kind of interface that let you work with the implementation of neural network processing that you prefer. So if you prefer to work with TensorFlow, you prefer to work with Tor, you prefer to work with Theano, there is no problem. Keras is kind of a wrapper, kind of an interface that lets you work in this way. So one of the nice things is that DeepLearning4J also supports Keras models. So in some way, everything you do with these libraries can be imported to DeepLearning4J and keep working on with this library in Java. I think Artur didn't talk more about reinforcement learning. I'm not going to talk about it, but one nice thing of DeepLearning4J is that it supports with another component called L4J, supports working in a very powerful way with reinforcement learning. I guess probably we will talk a little bit about reinforcement learning. Artur is kind enough to do it. And of course, many of us expect when working with a Java library, this Java library is deeply integrated with the Maven cycle or model of working. You have artifacts published in public repositories, and you can work as normal as you work in the daily basis. What is the DeepLearning4J inside? DeepLearning4J is what we could say, simplifying a lot, is just a domain-specific language. So if you look at the syntax, how to model a neural network, you have several predicates where you can enhance a basic model of a neural network, okay? This is code in Java, but of course, if you look a little bit on it, it's quite easy to see that it should be possible to make the same codification in another format, like XML or annotation or any kind of technique that you prefer. So this is the default implementation, but it's already prepared to implement or to model in another ways where you might feel more comfortable. Okay? How does it work? Of course, you can look at the Java API that is quite big and complex, but to focus a little bit, one of the main classes, one of the main components of DeepLearning4J is a class that is called multi-layer configuration. Through multi-layer configuration, you begin to model your network. If you remember what Artur called, there's a concept that is called metadata that somehow defines the topology, the complexity, and the algorithms that you use to train and to model your network, okay? So all these metaparameters are configured through these predicates, like, for instance, number of iteration, the initialization of the weights, the model, the algorithm for activation, the optimization algorithms, and you can see, I think it's quite verbose. What are the main methods that you use if you want to introduce you to DeepLearning4J? Basically, when you work with a neural network, you do 4 kinds of activities. The first kind of activity is modeling your neural network. It's where you decide if you want to have 5 layers, 6 layers, 10 layers, with retropropagation, with no retropropagation, with a learning rate bigger or smaller. Okay, that's what in DeepLearning4J is called with the method build. After configuring your neural network, you build it, and then you already have a neural network that is ready to be trained. Once you have this network, you train it with the method feed. Of course, the method feed expects to have some data set or some kind of input. In the case of where to explain it, maybe a labeled data set, and you input or feed your neural network through this method, and you get some result. You begin to train it, okay? When you think your neural network is already trained and is able to make the prediction as you expected, you can export your model with the right model, and you can import your model in another scenario, let's say in another virtual machine, or if you want to talk in terms of the life cycle of the development life cycle, you can think about training your model in a development or integration scenario, and when the model is ready to be used, you can export it and import in a production environment. Okay, that would be more or less the way to approach it. And finally, when your network is trained and exported and is ready to be used in some environment where you want to issue it, using the method predict, you then are forcing your neural network to react with data sets that were not part of the testing data set, okay? So this would be a very simple approach to start working with DeepLearning4J, building the network, training it, exporting it, importing in another environment, and then seeing how it behaves using the predict method. Of course, there is more and more and more in this library, but this is a very, very simple and focused approach. We already talked about the possibilities of visualizing the training process and the predicting process. Okay, that's what concerns DeepLearning4J. One of the reasons of this speech is that Artur and me wanted to see if DeepLearning4J was a library that is mature enough to be used in a Java environment, in a Spring environment, and trying to give a time to market very fast when using neural networks in production environments, okay? One of the problems, I don't know if it's exactly a problem, but one of the concerns that you have when working with neural networks is that it might take a lot of time to train a neural network and have it ready to be used in production environments. We talk of months and in some cases of years, okay? So if we want to use neural networks in production environment with the time to market that you are used to handle nowadays, it's clear that this approach doesn't probably suit all the customers' needs, okay? So we wanted to think in a method where, in a solution where we can work with neural network, but with low time to market times, okay? Then I need to make an introduction. After all, I will explain you the solution or our approach, but first of all, I need to explain you about the Spring Boot Actuator. I don't know how many of you know about the Spring Boot Actuator. One of them is that we many times have when building applications, Spring Boot applications, could be one of the situations, is that we need monitoring capabilities, but we don't want to lose time developing monitoring capabilities. We want they to be at hand for us just the moment we begin to develop. Fortunately, if you work with Spring, we have a feature that is called Spring Boot Actuator. Spring Boot Actuator is a feature through which you can collect lots of information about the behavior of your application, and then you can visualize them, or you can publish this information in a standard manner, okay? Spring Boot comes with several, I think it's about 20 or more, I think it's 20 or more actuators that gives you some information about the activity of the application. For instance, usage of short database connections, usage of several methods, the time consumption, weight of the responses, and all this kind of information that we are used to handle when we want to see what's going on with my application. apart from these pre-built actuators, you can build your own custom actuator to monitor other information. So the approach that we wanted to, that we thought was nice was have a system that have a neural network, but we want to see how the neural network is behaving in our production environment, okay? So we thought it would be a nice idea to develop a custom actuator that can monitor the neural network using the capabilities that DeepLearning4J already have to monitor the behavior of the neural network, okay? So we worked in a model that is, this is a schema of the model that we are using. We have a service that delegates, we have a service that has some feature or some business process in our application. We have, throughout, we make an interceptor that provides some information to an information service. This information service is the component that provides information to the custom actuator that is the component responsible for providing us monitoring information. You can use either the HTTP or JMX protocols to consume this information, okay? And this is not specifically supported by the Spring Actuator, but it's quite easy to write this. You can make that the custom actuator not only consumes information, but produces additional information. This is what we implement through the injector service, okay? So this would be a normal scenario to use a Spring Boot Actuator, okay? Then we are going to explain you how we model the application an application that is still in progress, is not yet finished, but that uses this approach to use a Spring Actuator. Okay? So I think it's better to go directly to this image. I think you will understand better what we are thinking about. Our strategy was being able to provide a neural network that is able to make some predictions, probably not perfectly, but that accurate enough to be able to go to production, but while being in production, producing additional neural networks more sophisticated that are able to make predictions more accurately, and in production, without the need to make additional deployment, substituting or replacing this neural network with enhanced one. Okay? So, which is the strategy? We think about a business process that delegates its behavior in a neural network. That's what we call the current network, the current neural network, okay? When we call the business process invokes the actuator service that, if you recall, is the service where the actuator itself relies on. The actuator service delegates the execution of the business process in the current neural network, but at the same time, the actuator service is producing in a loop that we could call endless, is producing enhanced neural networks, okay? This enhanced neural network is in production, in background, to say in some way, is being trained with the predefined training data set, okay? So when the enhanced neural network is already trained, we replace the current neural network with the enhanced neural network, okay? Of course, we have some ways to analyze or to decide if the enhanced neural network is better or not than the current neural network. But if we decide that the enhanced neural network is better than the current neural network, we replace it. So after this replacement, the coming business processes will delegate the execution in the new neural network. What happens with this neural network that has been replaced? We don't destroy it. We put it in what we call a pool of voting neural networks. One of the problems that we have also with machine learning is that not in all situations is possible to get data sets big enough to make the training, okay? If you want to solve a problem that has been studied a lot, it's quite easy to get data sets. But if you want to solve a problem that has not been studied a lot, you probably won't be able to get big and accurate data sets, okay? So we wanted not only to be able to have a low time to market, but also be able to produce data sets apart from the training data set that other people could use to produce additional neural networks, okay? So our strategy was, instead of destroying the former neural networks, we are storing them in a pool, and every time the business process has to make a decision to through the current neural network, we also ask all the neural network that has been archived, what do they think about this new input, okay? Everyone produces a response and use an answer, and using the answers of the neural networks, if we reach a threshold of agreement, then we decide that there is a big probability that the answer is good. So instead, in this situation, we take the input data and we take the answer, stored both in a new data set, okay? So as time passes and as the system is in production months and months, we are able to produce a very big data set that could be used for by other people, okay? So this is basically our approach. This is a process, this is a system that has a work in progress. We already make some advancements, but it's not yet finished. But we expect to be able to publish it in GitHub in the coming months, okay? I don't know if I've got enough time. Yes, I think so, okay? So this is what the talk was about, introducing deep learning for Java, introducing machine learning, explaining you how one possible approach to use neural networks in production-ready systems related to the business component, not to the scientific and academic side. But we have other motivations. We think that machine learning, this is a sentence I said during the last months to many people. It's my opinion, and I think it's the opinion of many people, that machine learning has come here to remain with us. As you know, in the past decades, machine learning tried to be a technique that could be reliable and powerful and usable, but it failed many times. Sometimes because there was no enough processing capabilities, sometimes because there was need much academic work to solve some problems, for instance, finding a local minimum or a global minimum. But nowadays, we are seeing many improvements that convince us that machine learning has come here to stay, to remain. So my advice is that you adopt machine learning because it will be a technology that will stay here for the coming months and for the coming years. I'm sure that in the coming months, machine learning will introduce more and more and more, not only in very specialized and specific problem solving, but in business processes and business applications as we're used to work in the normal day. Okay? So I have some recommendations, some advices to make to the Java community and to the Spring community. To the Java community, I'm convinced that the Java community should begin to explore the possibilities to model some of the functionalities of the virtual machine using neural networks. The one that comes to mind more easily is trying to improve the garbage collector algorithm using machine learning techniques. As for Spring, I already told you that Keras is one library that acts kind of a wrapper for all the Java library, for all the libraries or most of the library to work with machine library in the actuality, okay? But Keras is made in Python. I think we need a Java library similar to Keras, but modeled in Java. I think Spring has a very nice and very good opportunity to consider seriously making, as he already did, as Spring did already in the past for many and many functionalities, Spring has a good opportunity to consider seriously working on the wrapper that would let all Java developers working in Spring with machine learning in a very easy and attractive way. Okay? So that's my recommendation. Java developers, Spring developers, please embrace machine learning and push to the Java community, push to the Spring community to introduce more and more and more machine learning in our daily work, okay? And finally, and that will be the end of the speech, I want to tell you about AlphaGo. I don't know how many of you know about AlphaGo. AlphaGo, for me, AlphaGo, if you don't know, it's a program based in deep learning built by DeepMind. It's a Google company. I've been a Go player for more than 30 years. When I began to play Go, most of the people in my community thought that it could never be possible to make a program that could be top professionals Go player at Go. Okay? It was believed that Go was too complex to be solved programmatically. Probably 1 year ago, DeepMind through Google published AlphaGo. This program was able, as you see, I think this is impressive. First of all, AlphaGo was tested against the strongest Go programs in the world. It beat all of them. It was able to win 500 games in a row without not even one loss. When the team that worked in AlphaGo thought that the program was powerful enough, they wanted to test this about a Go professional, an European Go professional. Actually, he's Chinese, but he has been living in Europe for many years, Fan Hui Chudan, and beat him 5-0 in a match of the best of 5 games. After this, AlphaGo DeepMind wanted to go for a bigger target, and they matched the program against the strongest Go player in the world. Lee Sedol is a Korean Go player, 9-9, that won many international titles. AlphaGo beat this human Go player 5 games to 1 loss. The team that worked on AlphaGo was not still satisfied. They worked to meet AlphaGo even stronger and worked on a new version. This version was tested secretly in Go servers that you can find around the internet, and was able to win 60 games in a row against top professional Go players without even 1 loss. Okay, and if you get excited about AlphaGo, I'm really very excited. I'm sure you can notice it. At the beginning of the next week, there will be a new match between AlphaGo and the strongest Go players in China. There are scheduled 3 kinds of games. I invite you to visit the DeepMind website, where you can find lots and lots of information. I explain all of this to you because AlphaGo is based on deep learning. This is what deep learning is able to make nowadays. I'm sure, please believe me, deep learning is really very, very, very powerful nowadays. Embrace it. Thank you.